Good morning. Today we're looking at our first homework assignment on acids and bases. So the first question is looking at how we define acids and bases, and we've got two different definitions. We have the Arrhenius one here, which says we make H plus ions, that's acids, and base uses OH minus ions. So that's just a very simple definition. That's the Arrhenius definition, and that's what part A is asking us to classify. So HCl will produce H plus ions that can split up, so that would be an Arrhenius acid. HClO can also produce H plus, because then you'll be left with the ClO minus polyatomic ion. And H4OH can contribute OH minus to solution, and you'd be left with NH4 plus, which is the ammonium ion you recognize. So that's going to be an Arrhenius base. This is going to be neither, and you might say, well, how do I know that this produces H plus and this one doesn't? Part of it is you're looking at what's left over after I have donated the H plus or the OH minus. And you recognize HCl could split up into H plus and Cl minus. And Cl minus as an anion is perfectly legal. You've seen that all the time. In fact, chloride likes to be a -1 charge. It's perfectly happy with that. If you tried to do that with CH4, if you removed a hydrogen and a positive charge, you'd be left with CH3 minus. That's a polyatomic ion that you have never seen before. And so based on the polyatomic ions that you've memorized and the exposure you've had to lots of different compounds and ions, I would expect you to say, well, I haven't seen that, so I don't think that's going to be valid. You've got to apply that. Here for this next one, I've got zinc with 2 hydroxides, so you can see how that would donate hydroxides to the solution. Next, lithium hydroxide, same story. You'll donate hydroxide to the solution. H with NO3, you'll donate hydrogen. You'll be left with nitrate. That's a legal polyatomic ion. You've seen it before. This would give you potassium and nitrate, so it's not going to donate H plus or OH minus to the solution. HBr will donate H plus to the solution, and that's going to donate hydroxide to the solution. So you're either looking for H pluses or OH minuses, and that's the Arrhenius model. Now, a Brnsted-Lowry model is slightly more robust or slightly more expanded than the Arrhenius model. It still says that acids donate H pluses, but they don't. It also recognizes that in water, if you have H plus in water, it's not actually just running around by itself as H plus. It's attached to the water. In this form, we call that a hydrodium ion, and water will pick up that hydrogen to make this H3O plus ion. So the acids are pretty similar. I donate H plus to the solution. A base is slightly different in that I can accept a hydrogen. So hydroxides qualify as Brnsted-Lowry bases because they absorb hydrogen ions from solution. But we also have an expanded definition of bases as other things which will also pick up hydrogen ions. So they are hydrogen ion acceptors. Sometimes we call this H plus ion, that hydrogen ion. Sometimes we call that a proton because a hydrogen only has 1 electron and 1 proton. So if I have lost my electron, then I'm really just a proton left over. So these acids are proton donors, these bases are proton acceptors, and nitrogen works particularly well as a proton acceptor, and even water can do that as well. So let's see, down here, Part B, we're going to classify them as Brnsted-Lowry acids or bases. Again, if we see hydrogen ions that can be donated and conjugate bases left behind that are familiar, like in this case the hydrogen sulfate ion or the sulfate ion, then those look like acids. Iodide ion left over after you've donated that hydrogen to solution looks legal. Same thing here. Now I've got a nitrogen here. I'm going to call that a base because often nitrogen containing molecules act as Brnsted-Lowry bases. And again, we know that these are not acids even though they have hydrogens on them because we don't recognize the polyatomic ions that remain behind after I donate a hydrogen as something that you've seen before. So you can imagine NH3 picking up a hydrogen ion and becoming NH4 plus. That's ammonium. You've seen that before. But if I donated a hydrogen ion, I would be NH2 minus. You've never seen that before. And indeed, that's extremely rare. NABR would be neither, and same as CCl4. I'm not going to donate hydrogens because I don't have hydrogens to donate, and I don't really have room to accept a hydrogen in either case there. Conjugate acid-base pairs are ones that differ by one H plus ion. And if we scroll back up here, you can see the HCl is the acid because it's donating the hydrogen. The water is a base in this case because it's accepting the hydrogen. And so then this is the conjugate acid of that base. This is the conjugate acid of that base, because if I went backwards, then this is the thing that's donating the hydrogen. And this would be the conjugate base of that acid because it's the thing that would be accepting the hydrogen. So acid, conjugate base, differs by one hydrogen. Base, conjugate acid, differs by one hydrogen. So that's what we're looking at down here. If I have C2H5NH2, I'm going to differ by one hydrogen. I'm going to add a hydrogen with a positive charge, so that's going to be C2H5NH3 plus. That one right there. All right, some molecules can go both directions. That is, they can act as acids and they can act as bases. So here is just showing, and I'm not telling you where that equilibrium lies, but it's showing that this can act as an acid by donating a hydrogen to the water. You're left with a conjugate base of that original acid, and now the conjugate acid of this water, which is acting as a base. Or that HSO4 minus can act as a base by taking a hydrogen from water. If it does that, it forms the conjugate acid here, and then this is acting as an acid because it's donating a hydrogen. And there's the conjugate base that we're talking about. So in order to know which one is acting as the acid and which one is acting as the base, you're going to look carefully to see which species is losing an H plus in the forward direction. That's the acid, and the thing that is gaining that H plus is your base. So looking here at this example, we have HPO4 2 minus, and here I have H2PO4 minus. So it looks like I've gained a hydrogen, and you can also see I've gained a positive charge because now I'm not quite as negative as I was before. So this has accepted a proton, that makes it a base. Therefore, this must have been the acid. Now my base goes to form the conjugate acid, and the acid goes to form the conjugate base. And in this case, I'm going from HPO4 2 minus to PO4 3 minus. So I've lost a hydrogen and I've lost a positive charge. So having donated that hydrogen, I must have acted as an acid. That means this was the base. My acid goes to form the conjugate base, and the base goes to form the conjugate acid. So that's how we label each of those things. Now they want to know if these salts are going to be acidic, basic, or neutral. And part of answering this question is going to be memorizing which acids are strong acids and which are weak. And that is something you will have to memorize for this upcoming exam. So these are the ones that are strong acids. We have HClO4, H2SO4, HI, HBr, HCl, and HNO3. Now, a quicker way maybe to remember that is we've got I, Br, and Cl. These are all in group 7. So kind of group those together and remember that those are all very strong acids. And then you've got these three that all come from polyatomic ions that you memorized. And so the nitrate makes nitric acid. You've probably heard of that before. The sulfate makes sulfuric acid. You may have heard of that before. And the perchlorate makes perchloric acid. You may not have heard of that one before. It's a little less common, but sulfuric acid and nitric acid, hydrochloric acid, you've probably heard of that before. These are all extremely strong acids. And what it means that they're strong acids is that when they dissociate in solution, like let's take hydrochloric acid, put this in water, we donate that H plus ion to the solution, we're left with a chloride ion, and this is not an equilibrium, okay? It doesn't go backwards. There's no real interest that chlorine has in picking up that hydrogen again. So the strong acids are called strong acids because they just go in this forward direction. They go essentially to completion. Therefore, this conjugate base doesn't really act as a base. Okay. Anything else, any other acid that is an H plus that is attached to any other polyatomic ion or legal ion that we could see, like for instance, if I have HCO3 minus, this is an acid because you can donate the H and you'll be left with CO3 2 minus, which is legal. Just like this. Because this is not one of our strong acids, then this is in equilibrium. So then this is a conjugate base, and it does actually act as a base because this is in equilibrium and it goes backwards. Okay, so that's what we're looking at here. If we've got here polyatomic ions or ions that are conjugate bases of these strong acids, then they're not really basic at all. And if I have polyatomic ions or other ions that are legal ions but are not part of this, then we're going to say that that would actually be a slightly basic solution. We're only talking about being basic and not acidic because none of these salts have hydrogen ions to donate. So I don't even have that option of being an acid because you don't have any hydrogens to donate. All right, so KF, then let's look at that conjugate. That is F minus. F minus is a perfectly legal, perfectly happy anion, but it's not one of these ones that would be so stable as to just say I'm happy by myself, I'm not a base. So HF could dissociate to form H3O plus and F minus, and that would also go backwards, which means if I put KF in solution, I'm going to get F minus ions. That's going to act as a base. That's going to be a basic solution. Same thing with Na2SO4. That first hydrogen can be donated, H plus and HSO4 minus, and that is forward direction only, perfectly happy thing. But HSO4 minus, when it donates a hydrogen, H plus and SO4 2 minus, now we've got equilibrium. This is going to act as a weak base, so that's going to be a basic solution. KNO3 has got nitrate. Nitrate is one of these ones that is so happy that that's not going to be basic at all. It's totally neutral. And same thing with the sodium bromide, because the bromide is so happy. It's just neutral. Next, again, identifying conjugate acid-base pairs. Let's see, in this particular one, we've got H3PO4 and water goes to form H2PO4 minus and H3O plus. And you can see here that this species is losing a hydrogen. I went from 3 to 2, and I lost a positive charge because I went from neutral to negative. So I lost an H plus, or donated it to somebody else. That makes this the acid, and this the conjugate base. So this is the acid, and this is the conjugate base. H2O went to form H3O plus, so it gained a hydrogen and it gained a positive charge. As the proton acceptor, that makes this the base. Therefore, this is the conjugate acid. Let's do it one more time. The H2PO4 minus goes to form HPO4 2 minus. I have lost a hydrogen and I have become more negative. So I lost an H plus. Having donated that H plus, that makes this the acid and this the conjugate base. This appears to have gained the H plus. I have gained one more hydrogen. I've gained a positive charge. That makes this the proton acceptor. That is the base, and this is the conjugate acid. In part A, we called this a base. In part B, we called it an acid. And we did say that that's amphoteric, means it could go either direction. That's possible because it has hydrogen that it can donate, but it has a negative charge, so that's going to attract a hydrogen in cases where it can pick one up. So it could either donate or accept, either way. So here we said that HPO4 2 minus was the conjugate base of H2PO4 minus. Conjugate base. And HPO4 2 minus is going to be the conjugate acid of PO4 3 minus. So it's the conjugate base of this and conjugate acid of this, because this has gained one more hydrogen with respect to that. All right, next, conjugate base for HBRO. If I lost an H and a plus, then all I'm left with is BRO and then a minus. The conjugate acid for CN minus, that means I have gained a hydrogen and a plus charge. So then I have a HCN, and there's no charge because the plus charge cancels out the negative charge. The conjugate base for NH4 plus, I will have lost a hydrogen, so I have one fewer hydrogen and one less positive charge, which means I am neutral. And the conjugate acid for H2PO4 minus, I need to gain a hydrogen, so that's going to make it H3PO4 and gain a positive charge because I'm getting an H plus, so it's going to cancel out that negative charge. Okay, which is what? We've got H3PO4, H2O. The H3PO4 forms H2PO4 minus, so it has lost an H plus. It was a base. So that's going to be this one. I'm sorry. Wow. Brain fart moment. H3PO4 goes to form H2PO4 minus. It has lost an H plus. Therefore, having donated the hydrogen, that makes it the acid. Okay, that's what I've been saying. All right, CO3 2 minus. Here it has gained a hydrogen. Having accepted that hydrogen, that means it was the base. CO3 2 minus, it was the base. And H2O was the acid because it's the one that donated the hydrogen. Okay, and H3PO4 going to form H2PO4 minus. That means this has donated a hydrogen because it's lost one, so it must have been the acid. All right, properties of acids and bases. Let's skip the litmus paper thing for a moment. Bases taste bitter. Acids can dissolve many metals. Acids taste sour. And bases feel slippery. So like soap is a base. So it feels slippery and it tastes kind of nasty. That's true. And lemon juice tastes sour. And also acids can dissolve many metals. That's actually part of the reason that, for instance, Coca-Cola dissolves all sorts of things because it has phosphoric acid in it. All right, in terms of litmus paper, this is really interesting, but litmus paper actually comes from a kind of lichen. That's where the litmus dye comes from. And it turns red under acidic conditions. So it's going to go here, and blue under basic conditions. Bet you didn't know that came from a lichen. That's kind of an interesting bit of trivia. All right, strong acid, strong base, weak acid, or weak base. I already gave you, here's the list of strong acids, and all other acids would be weak acids. The list of strong bases is much shorter. Anything with a hydroxide on it, particularly one that's going to be soluble, like lithium hydroxide, because all group 1 ions are soluble, that's going to be a strong base. So HClO4, that's at the top of our list of strong acids. That is acetic acid, that's going to be a weak acid. You could recognize that conjugate base as the acetate anion. This would be the formate, that's COOH, as it's a kind of organic acid. Here we've got a hydroxide. Hydroxides, usually strong bases. Amines tend to be weak bases. So that's where those NHs come in as Brnsted-Lowry bases, but they're going to be weak. None of those are going to be strong. HCl, list of strong acids. HCN, not on our list of strong acids, but it would still be an acid because it can donate the hydrogen and you'd be left with a cyanide polyatomic ion. Same story here, not on our list of strong acids, but it could be a weak one. That's on our list of strong acids, strong bases, strong acids, and strong bases. So let's try this and see if they'll take that. Okay. So again, you memorize the strong acids. Any acid that's not a strong acid is a weak acid. And for strong bases, you're just looking for hydroxide. Otherwise, if you see a nitrogen containing formula, that could be a weak base. Okay, characteristic of an acid or a base or both. Acids are sour. Acids react with bases, so they will neutralize them. Acids donate H+ ions in the water. Potassium hydroxide would be a base. And both acids and bases would be electrolytes because they donate ions to solution. Bases will neutralize acids. Bases produce hydroxide ions and water. Bases feel slippery. They both conduct electrical current. That's the definition of an electrolyte. And we said that acids turn litmus paper red. All right, so right now we're looking at solution concentration units. And this is actually nothing new. You have done this previously. We're just doing it with acids, so it's exactly the same thing. If I have HNO3, and I have this in water, donates H+ to the water to make H3O+, and NO3-. This is really just exactly the same as saying HNO3 goes to form H+ and NO3-. In aqueous solution, both of those are perfectly fine. But it's a little bit more accurate to call it H3O+, because if I'm in water, this is really attached to the water molecule to form the H3O+. But let's say I've got 1.60 grams of this in 0.540 liters of solution, and they want to know what the H3O+ concentration is. You've got this reaction to follow, and this is a strong acid, so you know it goes to completion. And what we're going to do is convert from grams of this to moles of that, and then moles of this to moles of that, and then they want molarity, which is moles per liter. So once I've got moles and liters, I can just put those units where I want them and calculate the answer. So 1.60 grams of HNO3. If you consult your periodic table, you can find the molar mass, which is going to be 1 hydrogen plus a nitrogen plus 3 oxygens, and that's going to give me 63 grams in a mole. Next, moles of HNO3 to moles of H3O+. It's 1 to 1. You still have to include this in your dimensional analysis, even if it's 1 to 1, just so you can make sure that your units cancel. So I have moles of H3O+ on top, so I can put 0.540 liters of solution on bottom. That gives me moles per liter. So 1.6 divided by 63 times 1 divided by 1 divided by 0.540. That gives me 0.0470. Same type of problem. This is a concentration problem, exactly like we saw in our previous chapter, where we have sodium hydroxide dissociates in solution to form the sodium ion and the hydroxide ion. And if I have 0.225 grams of this in 0.230 liters of solution, then I have to go from grams to moles of this, and then I can go from moles to moles of that. And moles divided by liters gives me molarity. So 0.225 grams sodium hydroxide. And if you consult your periodic table, we've got 22.99 for sodium, 16 for oxygen, 1.008 for hydrogen. That gives me 39.998. Probably round that up to 40. Grams of sodium hydroxide cancel. Then again, 1 mole of sodium hydroxide produces 1 mole of hydroxides, ions. And we've got 0.230 liters of solution. So now we've got the moles of hydroxide in liters of solution. So 0.225 divided by 39.998 times 1 divided by 1 divided by 0.230 gives me 0.0244. So this section is looking at whether a solution is acidic, basic, or neutral based on the hydronium ion concentration. And it even gives us an equilibrium value, which tells us that these two things are actually related. So we can use that value, KW. Going to be the H3O plus multiplied by the OH minus. So knowing what we know about equilibrium expressions, we can predict that if this goes up, then that goes down, so that that K value will stay equal. And vice versa, if that goes down, then this goes up. And if we're at 1 times 10 to the minus 7th, then that's the middle. That's also going to be my OH minus. That's the point at which these two things are equal. But otherwise, if the H3O plus is higher than that, then the OH minus is going to be lower than that, right? And vice versa. So here, if the OH minus is 6 times 10 to the negative 12th, that is much lower than 1 times 10 to the negative 7th. That means that the H3O plus is much higher than 1 times 10 to the negative 7th, which means that that is an acidic solution. Now you don't have to eyeball it, you can actually plug it in, and here I'll show you. If we just plug this in, 1 times 10 to the negative 14th, divide out the hydroxide that we've got, which is 6 times 10 to the negative 12th. And we see that our H3O plus concentration is 0.00166, or 1.66 times 10 to the negative 3rd. That is definitely greater than 1 times 10 to the negative 7th. So again, that's acidic. So you can either plug this in your calculator, or you can eyeball it like we're doing here. We'll do a little bit of both. We can see here they give you all hydroxides. And so we have to do this and say, all right, if the hydroxide is less than 1 times 10 to the negative 7th, that is if this negative number is larger than 7, right? If I'm at negative 9th, negative 10th, negative 12th, all of those things mean that the H3O plus, because the OH is lower, then the H3O plus must be higher, and you're in an acidic environment. So negative 9, negative 10, negative 13, those are all there. 1 times 10 to the negative 7th, that means that these are the same, so that you're really truly neutral. And then these 3 times 10 to the negative 2, 7 times 10 to the negative 4th, 5 times 10 to the negative 5th. In that case, your hydroxide concentration is higher than 1 times 10 to the negative 7th. And so if this is higher, then that must be lower. And if I'm less than 1 times 10 to the negative 7th, then I must be basic. So those are going to go right there. So here is having us do that mathematically. If my H3O plus is this, then what's my OH minus? And that's where we say, well, if H3O plus multiplied by the hydroxide really is 1 times 10 to the negative 14th. And I know my H3O plus. I'm going to divide both sides by the H3O plus. And these, of course, cancel. I find that my hydroxide is equal to 1 times 10 to the negative 14th divided by my H3O plus, which in this case is 2 times 10 to the negative 6th. Just plug that into my handy dandy calculator. 1 times 10 to the negative 14th divided by 2 times 10 to the negative 6th. And by the way, if you haven't gotten used to using that EXP button, strongly recommend it. 5 times 10 to the negative 9th. It's going to prevent you from making a mistake that's going to cost you dearly. All right, and then to go the other direction, if I give you the OH, then find the H3O plus. Again, we're just going to take 1 times 10 to the negative 14th, 1 times 10 to the negative 14th, and divide that by the OH, in this case 2.7 times 10 to the negative 2, we get 3.7 times 10 to the negative 13th. Okay, and this is all exactly the same thing. If I'm telling you this is the OH minus concentration, then can you tell me what the H plus concentration is? Yeah, I'm going to just plug all these into this exact same formula, right? So in this case, I'm calculating the H3O plus to be 1 times 10 to the negative 14th divided by the OH minus. So 1 times 10 to the negative 14th. In fact, in order to make my life easier, I'm just going to hit memory store and say 1 times 10 to the negative 14th, which I'm going to use over and over, is stored into my memory. If I divide that now by 1.6 times 10 to the negative 2, that gives me 6.25 times 10 to the negative 13th. So 6.5 times 10 to the negative 2. Sorry, negative 13. Next, memory recall. That's 1 times 10 to the negative 14th. And now divide that by 1.4 times 10 to the negative 11th. That gives me 7.14 times 10 to the minus 4th. Right, starting over, memory recall, there's my 1 times 10 to the negative 14th. I'm going to divide that by 1.1 times 10 to the negative 5th. Now I get 9.09 times 10 to the negative 10th. And finally, seawater. Start with 1 times 10 to the negative 14th. Divide that by 2.4 times 10 raised to the negative 6th. Start with 1 times 10 to the negative 14th. Divide that by 2.4 times 10 to the negative 6th, and I get 4.17 times 10 to the minus 9th. So notice again what we were talking about here, that if the kW is 1 times 10 to the negative 14th, the only way that these two things can be equal or truly neutral is if each of those is 1 times 10 to the negative 7th. And if one of those is higher than that value, the other one must be lower, and vice versa. So -2, that's much higher than -7, so this is much lower. -11 is much lower than -7, so this is much higher, and vice versa. So this is doing exactly the opposite. If I know the H3O plus, then can I tell you what the OH minus is? And of course, it's basically the same formula. So in this case, we're saying the OH minus is equal to 1 times 10 to the negative 14th divided by the H3O plus. The two of those together equal 1 times 10 to the negative 14th. So I could even use my same little memory recall here. 1 times 10 to the negative 14th. Divide that by 1.5 times 10 to the negative 8th, and I get 6.67 times 10 to the negative 7th. Here, if I start with 1 times 10 to the negative 14th, divide that by 3.5 times 10 to the negative 4th. We get now 2.86 times 10 to the negative 11th. And if I start with 1 times 10 to the negative 14th, and I divide it by 5.0 times 10 to the negative 7th, I get 2 times 10 to the negative 8th. And last problem, if I start with 1 times 10 to the negative 14th, and divide that by 4 times 10 to the negative 12th, I get 2.5 times 10 to the negative 3rd. Okay, that is it. I hope that was helpful. Have a great day.